All right, so week 3 is nomenclature only on discussion menu. Got your quiz next week will be a combination of nomenclature and hybridizations. So it's not very hard as long as you do some exercise comparing to the quiz 1 that you're taking today. I think including week 2 and week 3 is not that hard. So I think the hardest quiz is the quiz that you're taking. Yeah, question?
This is just week 1, right?
What?
Is this on week 1 and week 2 or just week 1?
So quiz 1 will be only discussion 1, which is structure and resonance. I mean, hard means resonance. I think the resonance question on quiz is not easy, but don't feel painful that the second quiz will also be that hard. It's like we want students to start it harder. The second one won't be that hard from my perspective. Maybe not from yours, but that's just honestly speaking. So on the notes that I sent to you guys, so you should be able to see this one. Sorry. Okay, that's a field one. Okay, empty. This one. Topic 1 is untitled nomenclature, which you will be tested in the next week's quiz. Part of them. The other is hybridizations. The other is a little bit of week 4, because I personally think these two are highly related. Okay, I'll explain. So if we have the time to cover topic 2, only assign R&S, you might or might not have heard that before, or in the lecture part. If we got the time to do that, we will only learn this part. It's just from my understanding, these two are combined together always, so it's nonsense to separate them into 2 weeks. It also give you a better learning curve. That if you have learned how to assign R&S this week, by the time when I'm formally teaching stereochemistry in week 4, you already have a week of getting the concept of that. So it's a better learning curve, just from my personal perspective. Okay. But anyway, let's start with nomenclature. So you learn how to draw correct structures for organic compounds in week 1. Now you should also learn how to name them. Starting from counting how many carbons you have. For each numbers of carbon, we give them a specific name that is listed on discussion menu, this page. So the first kind of name that you guys are learning are just alkynes. And the alkyne names, which is listed here, the whole thing, and with A-N-E, so you probably can see they all end with A-N-E, which is consistent with alkynes, is the first kind of name you're learning. With the increasing of carbon numbers in alkyne, each of them have a name. So you should, starting from now on, if you have 1 carbon, you will see methane. In the future, if it's a different functional group, the things changed will be only the last a few letters. Well, meth, this one, M-E-T-H, you're going to see this one all the way through your organic chemistry. So you should try to learn. This is the only memorized part of nomenclature of organic chemistry, which we will only test you until 12. So that's why I circled these 2. Okay, we'll only test you up to 12. So any carbon number smaller than 12, including 12 carbon numbers, you are responsible for their alkyne names. Did I make this point clear? Okay. So assuming you know the number accordingly, then what's else? So we will start to name them. So that's stepwisely on discussion menu. We stepwisely learn how to change an alkyne into something else. Here you see they change a methane into a subgroup, which means if you see a CH3 group bonded to something else. So I don't know what's this one, but I know how to name this part, the red circle part, accordingly, which this name changed from methane, which is the 12 names I asked you guys to remember. Something end with A-N-E. You change the A-N-E into Y-L if we want this one to be the substitute. Okay? So accordingly, you are going to learn a bunch of that. These names are substitute, so that's come to the second concept. When I'm going to name my compound with A-N-E, or when it's the time to change the base name of this compound. So I passed around a handout that is made by one of the tutors. You probably guys, so I'll come to this one. Okay, I'll send this thing. Okay, give the picture can okay. I've passed around a handout, so I hardly pass around anything. If I pass around anything, it means you better tape it on the wall of your desk or something else, some place that you can see all the time. And because today's exercise that we're going to do in the class, I want you to have this one next to a pad or next to a note, so you can compare it side by side. Does that make sense? So that's the reason I print out something for you. Although you guys are only responsible for naming of alkyne, well, including hollow alkyne, so which is here, alkyne. So let's find alkyne. Alkyne's here, okay? And a little bit of ether. So I'm talking about whole 118A, not the next quiz. Next quiz is going to be just alkyne and hollow alkyne, okay? Alkyne, alkyl halide, which is hollow alkyne, ether, and alcohol. So those are 118A. Okay, but I know, oh, you guys cannot see it. Okay, sorry, my bad. Okay, so only the chapter compound are the chapters that you are going to learn in 118A. But I don't want just to teach you like name chapter by chapter. The reason I put this table here is there is a priority, which is going to give you a choice on which name that I choose to use as base name, which is here, base chain. If I see a functional group in a higher rank, so you guys probably have learned functional group in your lecture parts, right? You should, right? Learn all kinds of functional group in your lecture part. I believe she has already got through the page. Okay, if you see something different than alkyne, that's probably a functional group. Like you see OH, you see SH, you see cyano group, whatever. So whenever you see them, how you are going to choose? If I have a compound have several functional groups, you always name the compound with the highest priority, the functional group that has the highest priority. You choose that one as base chain. And what does those dash mean? That means when you were changing, every name comes from alkyne, okay? For example, if I have 3 carbon, then that's propane on your discussion menu. So the third one is propane. Then you change the ANE, so wipe out the ANE and change accordingly to the base chain. So that comes to all the examples. For the rest of them, if your functional group is not the highest, you also have other functional groups, then you name them as substituents. Those substituents were also named accordingly with the alkyne name. So you change them into the substituent format. Only if that functional group is the highest functional group of the whole molecule, then you name it, you choose whatever that's named under this column of as base chain. So that's, from my perspective, that's the whole part of nomenclature of organic. I use this table myself, and I put this in front of my desk even now. So if I need to name it, that's done. So I don't have to go through each chapters to learn the nomenclature. Does that make sense? So this table, you can save it for the future 118 use. It's not just for 118. Okay? Okay, now let's come back to the, okay, so which means today's content was also included in this table. Okay? Okay, let's come back. So that's why you are going to do the change. And I show you the table when you do the change accordingly, and how to choose the correct format for the change that you need to make. Make sense? But all the change were only in the last few, but you always keep consistency on how many carbons you have, and only just wipe out the ANE, change into the whatever base chain or substituents that it's required to. Make sense? Okay? That's for the naming. Okay, that's for why you need to memorize alkyne name and how to change it accordingly. Okay, and those are IUPAC name. But apart from the IUPAC name that we might test you in the quiz, we also give you common names which we don't test you, but we want you to recognize them when you see them. Okay, for example, if you see a bunch of things, X. Okay, here it's a different one. Okay, X doesn't mean halogen here. X means something else. It means I'm only talking about the group here, which is this group. Okay, this group is the group that I'm circling. Okay, X is not halogen, only in this example. Okay, so when you see this part, if I'm going to name it according to IUPAC name, although I haven't teach you how to yet, but let's just do a small exercise on this one. So here are 2 carbons. So from my point of view, this methyl is the substituent of this 2 carbon chain. And if we come back to 2 carbon is ethane. So this blue chain is ethyl, okay, ethyl. Well, this green one, okay, this green methyl is substituted as the number 1 carbon, 1, 2. Okay, it's 1 methyl ethyl. Okay, the reason that is YL is I changed the ANE into YL if they are used as substitute on your table. Okay, so this name, this group has a name of 1 methyl ethyl. If I need to name it according to the rules I just teach you, the table. However, we usually call it as isopropyl. So that's the common name. The table listed here are only the four, in 118 series, the four only common names that you need to know. Okay. For each of them, I can write their IUPAC name, for example, this one, because I have 1, 2, 3. I have 3 carbon, and I treat this one as a substituent. So this substituent, which is a methyl group, is 2-methyl, and its base is a substituent of 1, 2, 3, which is propane, so propyl, okay? So this whole group has the name of 2-methyl propyl, but we usually call it isobutyl. So that's some common names. It's different from IUPAC name, but we want you guys to recognize them. We probably won't test you. We won't ask you to write correctly in an exam. As long as you write IUPAC name, it's always correct, which means the table name I showed you. But we want you to be able to recognize, okay? Okay, and keep going. Oh, okay. Actually, they write the IUPAC name for some of the example. So the 1-methyl ethyl, 2-methyl propyl. Okay. So those names were some of the examples. But as I said, it's still that 4 that you need to know. Okay. Okay. And then how to write IUPAC name, which is the table. Okay. So I also put this one on my notes, which is what is LLA rules. Okay. The first L comes to the longest chain of continuous carbons, which means you need to find the longest base chain. So on my table I still put as base chain in the table. It's not my table anyway. It's EDNA. I don't know how, but that's the Larson. I think it's ED Larson. Yeah, it's Dr. Larson's table. In Dr. Larson's table, she puts as base chain. Okay, base chain on the table is also relevant to the longest chain continuous carbon here. That base chain has to contain your highest priority group, which means has to contain your family group, not the rest of them, but has to contain the highest one. If I have a longer chain, but that longer chain was not on the way of, well, my family group was not included, then even I have a longer number, continuous carbon number, that is not my family chain, okay? So this one, find the longest chain of continuous number. It's just because discussion manual only teach you alkane. For alkane, the functional group is alkane. So there's no need to include family group here. But I teach nomenclature as a whole part, just to let you know. Okay. The longest continuous carbon chain containing family group. That family group is the highest priority group that you can find in this molecule. Okay. The second L is the lowest position number. Okay. So it's writing in this way. So when you have a chain, usually you name it either from left to right or right to left. Label it, number it. Okay. Then the number, here it compares number by number. Okay. If the numbers are the same, goes to the next nearest substituent. If the numbers are exactly the same, then compare until you see a difference, which means in two directions. In either way, you can find a lowest position number to number all those substituents. We're going to see an example later, so don't be confused. But anyway, so here is another example. If either you count from left to right or you count from right to left, they have the same. If they have the same number, okay, then it's the same regardless of the direction. Then the lower number goes to the first substituent in alphabetical order. We're going to see an example on discussion manual later. But anyway, the second L goes to the L for lowest substituent number. We are always aiming for, in whichever direction that I can name my substituents in a lower number, then we go with that direction. This is quite tricky, and you can see from my notes, I give you several very similar examples, and that's where this lowest, the second lowest, comes to, well, it's tricky on which direction to choose, okay? And the last one is just name all substituents in alphabetical order. Okay, so LLA rules, I also copied that on the notes. We'll come to that with exercise. Okay. Okay, here are some examples of the special case. So let's go to let's quickly read through them, then we go to our notes. Okay. The first example, this non-name is because we have 9 carbon, okay? We have 9 carbon. If you count, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 9 carbon in this family chain. And you're going to ask, why don't you label this way? Because there is a substituent, right? I can, if I choose my family chain in a green line, then this one, okay, this purple is gonna just to be a ethyl group. But if I choose the purple line as the main chain, this is going to be a little bit complex substituent. So I choose the way that's easy. Okay. Okay. And this one can be quite obvious. So that's okay. The first are just how to choose family chain. Here the example, this might not be a good example, but the family chain has to include functional group. In this case, in hollow alkyne, then it's the halogen. Okay. Okay. And this is a good example on how to choose the direction. Well, because they all, okay, so it's not very obvious if they just write like this. Left to right, if we count from left to right. So the substituents was number 2, chloro, number 3, ethyl, number 5, methyl, number 7, ethyl, and number 8, okay? If I count the other way, from right to left, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Now it's the same. So see, substituents, it's the same. But that's where you need to choose which direction. So that's the very, not very normal scenario. That's when you count either way, they count the same. Usually you can have a lowest on one direction. But this is when they tie, when they are the same, then the first substituents from left to right is chloro. So it starts with C. And if it's the other way, it starts with M. So C comes first, so we choose to name it from left to right. Make sense? So this is also part of the lowest position number, okay? So the example next door is where you can differentiate, okay? If it's 2, 5, 6 on one side, and it's 2, 3, 4 on the other side. When we go to 3 and 5, it's already decided. Even I know later they probably is going to be different. So even I have 6 or something other number, it might be smaller, but well, usually don't. But when I see the difference, the game is over. Does that make sense? So when I see 3 and 5, we compare that. When we see a difference, the game is over. No matter the rest of them. Make sense? Okay. So that's how you count the lowest position number. And the third step is just to put them in the alphabetical order. So you can see in either way, their number doesn't matter. What matters is their alphabetical order. Okay, something special. Okay, this die. Okay, because we have 2 ethyl group, number 3 and number 7. Okay, number 3 and number 7. This one and number 7, they are both ethyl, so it's diethyl. Okay, this di, including the tri for 3 and other, they don't count in alphabetical order. We count E here. We don't count the di, okay? So the thing that really matters is the ethyl and the methyl. Actually, they're also missing a di here because we have 5 and 8. Okay, this discussion, there's a typo. It's missing dimethyl. Make sense? Okay. All right. So that's the discussion menu, and you can have a play with the rest of them. Okay, now the second one is when we have a ring. Okay, it's a change in the year 2018. That's if we have a ring. Previously, if we have a ring, we treat the ring. I mean cycloalkynes. Okay, cycloalkynes. If we have a ring, we just treat them as normal alkyne, which in our table they are going to just to set in the range of alkyne. But after year 2018. We change our way to name it into whenever we see cyclohexanes, that one is always going to be the family chain. Okay. In your quiz, you won't see question like that because we are considering some of the students are like taking organic class from long time ago, so we don't test you on cyclo things in the quiz. But it just gives you a time to be prepared that there's a change in the rules of IUPAC nomenclature. But if I also write that on my notes. if you see cyclohexane, no matter what are the rest of the functional groups, cyclohexane always win. Okay, so that's why I'll point out specifically. All right, when you name cyclohexane, okay, cyclohexane is always going to be the main chain. Then when you number the rest of them, okay, let's say starting from one side, okay, 1, 2, 3. Well, obviously 1, 3 is a smaller number than 1, 2, 3, 4, 5, than 1, 5. So we will choose to name the ring with 1, 3, right? So that's very obvious. This is the lowest substituent number. Okay, and did you still remember we talked about wedge and dash, which is when you see the bond is pointing out for wedge, or the bond is dashed into the paper, if both of them are on the same side, which means both bonds, okay, we are only talk to the bond with the scenario with this cyclo stuff only have 2 substituents. Okay, we're only talking about the scenario where this cyclohexane only have 2 substituents. If they are both pointing up or both pointing down, they're in the same side, it's cis. Otherwise, it's trans. For example, this one, it's trans. Okay, well, we are not talking about this one though. Okay, if we only have this, the bottom 2 substituents, then they are trans. And okay, you already start to see S in this name, and that's why, in my perspective, nomenclature should including assign R&S. That's something to do with this chiral center. Okay, the carbon labeled with S. If you just S. Okay, if I draw out all substituents, all the bonds that this carbon has, this one is a dashed hydrogen, and this one is a wedged hydrogen. Either of these blue carbon are bonded to 4 different stuff. We call this kind of carbon chiral center. And R and S are used to indicate if this chiral center is type 1 or type 2. We'll come to this in the second topic. Okay? A complete nomenclature will include indicating any stereocenter show up in this molecule. Okay? Actually, the most common mistakes that students make in nomenclature is not they choose the wrong direction. It's not they didn't name it according to the alphabetical order. It's they forgot to put R and S in the front. That's the most common mistake. And that's why I want to teach you how to assign R and S in this way. So you memorize that. I teach you as the whole thing. Okay? Let's move through. Okay? Here they list several examples on how to write the name accordingly on the cyclohexanes, which I think is basically the same as the LLA rules. You can read through that. And we come to the practice. So the practice this week will be all kinds of the nomenclature. Either you write the name of the compound or you write the compound from the name. Okay? In here, because we haven't teach you R and S, so you will only see trans and cis. No cis? Oh, here's one. Okay. Okay, now, because you have uncertainty in the back of this menu, I'll go to something that I think is important. Okay, so let's review a little bit. This, for example, this is a compound. Okay, this is on my notes. This is a compound, and the moment you get the molecule, although I have listed the correct name here, you are going to the first thing you do, although you only learn one functional group, which is halo alkyne, the halogens are the functional group. You start to circle them. Okay, that's bromo and chloro. Okay, that's the functional group. And did you still remember that our family chain needs to contain them? Okay. I meant to design this molecule in this way, or write this molecule in this way. So if you count the other way, okay, here, this blue chain is the same carbon number. But as you can see, if you after we finish talking about this example, the green chain is the family group. It's the green chain. The compound was named under the green chain. So that's a common mistake where students always forget to include those halogens into the family chain. So they just go for the longest carbon number, but forgot you also need to include family groups. Okay, that's the first common mistakes. All right, after that, you start to think about in which direction that I should start to name with. So either 1, 2, 3, 4, 5, 6, 7, 8, 9, or from the other, from right to left. 1, 2, 3, 4, 5, 6, 7. Huh? Huh? White. Huh? Yellow. well, on discussion menu, it's well on the name here that I already list the correct number for them, so you should be able to easily figure out. It's named in a yellow way, which is here is 27. Okay, I'm going to put the according number of the red direction. Okay, so the chloro will be 3, and the bromo will be 8. Okay, and this is still going to be 5. The 3 methyl group, okay, methyl, and methyl are 3, 4, 8. Okay, 3, 4, 8. Okay. All right, I'll start with the first one. So you can continue on the rest of them. Okay. The first one, because we talk about as long as you have a ring, then your ring always wins. So the functional group of this compound has to be cyclohexane, no matter what. Okay. Although I also didn't put any halogens on that, but cyclohexane always wins. Okay. And the second point is, although I have wrote 6-ethyl, 6-ET, I managed to do that in this group, but actually this blue one is part of the main chain, right? We might put questions like that, but honestly speaking, I think this is tricky. It's my bad to make the question as tricky as this one. There are 2 more carbon on this ethyl, so you should count this blue ethyl as mentioned instead of the substituent. Make sense? You're going to hate the people who design this kind of questions, but it's better you see them here rather than seeing them in exam directly, right? Okay, so here are 2 carbon here. So some people can even not write this octet, which is for 8 carbon. Some people would write hep, which is for 7 carbon. So that's wrong already in the base chain. Then your naming might be wrong for the rest of the time. Makes sense? So make sure you find the longest family group, longest carbon chain for family group. There are 8 carbon, okay, in this case. So 8 carbon, 8 is oct. Makes sense, right? Okay. So the rest of 5 green ethyl. Okay, the rest of 5 green ethyl are 5 ethyl. Oh, sorry, 5 ethyl. So 5 for pent. So it's pent ethyl. Okay, pent ethyl. Because cyclohexane is the family group, so there are only well, it's not the only. So it's either clockwise or anti-clockwise. In our case, in either way, this whole blue stuff is a substituent. So for substituents, you don't think about, do I name from one direction or the other? You always name the substituents from the closest carbon to the family chain. In our case, our family chain is this ring, and it doesn't matter if you count either way. This is going to be number 1. So the closest carbon on substituents is going to be number 1. And the 5-ethyl, you name them accordingly, which is number 3, 2 on number 5, 2 on number 6. So 3, 5, 5, 6, 6. Pent ethyl. And then you count the methyl group. There's only 1 methyl group, which is here. Okay? So number 3, methyl. Oct for 8 carbon. 1 for En, although I haven't teach you guys, but it's also on the table. So 1 for En for double bond, which is here. The smallest number, my carbon double bond has 2 carbon. One is carbon number 1, and the other is carbon number 2. I always name it in a lower position number. So I name my En, which is for double bond with number 1. This purple YL is because I treat the whole stuff, this whole blue stuff, as a substituent to my cyclohexane. So this YL, I write them in purple, because I treat the whole stuff as a large alkyne substituent to cyclohexane. So it's N with YL. Okay. I know this is kind of complicated. Your quiz probably won't be that hard. Like the tricky ethyl I'm putting here, but it's better you see them here. Good? Okay. Now the example next for, I just removed the cyclohexane. I removed the whole ring with a normal carbon. Okay, so that's the only difference. And let's see if anything changed. Okay, so first, because I changed this ring into a normal carbon, now the whole chain, okay, 9 carbon chain become the family group. Oh, sorry.
I was wondering if you could know what YL is here.
Y what?
YL.
YL. Okay, so do you understand this part? So if I only have 3 carbon that is bonded to a cyclohexane, for example, okay, then this 1, 2, 3. Originally, this 1, 2, 3 was propane for 3 carbon. Now I changed propane into propyl. So it's a propyl bound to cyclohexane. Do you understand this example? So when I change an alkyne into a substituent, it's also on my table. So if you go to the table, alkyne, when they go to substituent, it ends with YL. Alkyl, so ALKYL, it ends with YL. Now I'm treating the whole blue chain as a substituent. So it's a substituent to the purple cyclohexane. So the whole blue stuff needs to end with YL because it's a substituent. Make sense? Okay. All right. So if I don't have a substituent, if it's just itself, see that's the difference. If it's itself, then you end with ANE or ENE. In this case, because the family group changed to alkene, so it ends with ENE. ENE is the named for alkyne as a base chain on my table. Good. Okay. Also pay attention to the small arrow that I'm pointing at the E. So this doesn't count in alphabetical order. Okay. And the two examples below, it's the same tricky thing, but I will also post this note, as you know. Yeah. The only tricky part, the similar tricky part, I would say, not the only. Okay. Similar tricky part would be, although I write like this, it's ET, but it's named. See carbon number 5. It's named as 5-propyl. Okay. Don't name the compound as what I write. Count the carbon number. Does that make sense? Because I have 1, 2, 3 as substituents. So I named the whole substituent as a group. It has 3 carbon. It's supposed to be propane. Now it's propyl. Make sense? So don't be confused on how we write it. Always count the carbon number. But you will hardly see a tricky question like that. But I put so many tricky questions in here, so you see the extreme examples. Okay? All right. From those examples, okay, diethyl, we count E. Trimethyl, we count this M. 5-propyl, we count this P. And put them in alphabetical order. All right. So if you compare all those 5, you will draw the conclusion of these 3. Okay. The rule of numbering, the first substituent carbon, okay, doesn't mean we always give number 1 to the family group. See here, alkene were also named under 2. I know some of the people will think if I need to have family group and I want my family group to have the lowest position number, then they will give alkene number 1. It's not always the case. Okay. The scenario that you have the lowest position number doesn't mean your family group needs to be number 1. It's a common mistake. And the second is di, tri, tetra, etc. They are not useful for alphabetical ordering. Okay, special case we will not cover yet. You will see them in future. Okay. For hydrocarbons, you are always going to name cyclohexane as base chain, which that's always going to be your family group.
Sorry, I have a question about
Yeah.
the second example.
Uh-huh.
Why did you, if the center chain is all included in the main carbon chain, why didn't you order it from sort of bottom?
Oh, you mean I didn't order like, oh, so you want me to count like
Yeah,
1,
yeah.
2, okay, let's count together. 3, 4, 5, 6, 7, 8, 9. Okay? If that is the case, well, the real reason is in this case your family group is going to be alkene. It's actually 7. Sorry. Okay. Your family group is going to be alkene. Okay. If you count this, let me count. Okay. If the other way, it will be 3, 3, 4, 4, 6. Am I right in counting? And 6. Am I right in counting? Purple. If you use my tricky method, you should be obviously seeing the purple number is higher than lower. Okay, but the correct way is you need to have a lower. You should give the family group a lower number. So number 2 win. But you can also test with my tricky method. You add them up, although I haven't, but I assume the top one will have a higher number. Okay. Okay, actually that's a good example. So here are two examples. Okay, I only have 10 minutes before you start the quiz, so I'll go through them quickly. Here are when you have a time, even you count them. If you count them, I add them up. When they have the same number, then whichever family group has a lower position number, whichever win. So this one, the yellow win on the left side, and the red win on the right side. I meant to let you guys exercise on this too. So all my examples are extremely similar to each other. It's just one carbon shorter. Then you are counting from one direction to the other. So that's some exercise that you can practice on. I will give you the answer, but you can try to figure out why it's even I just cut off one carbon, that is one is right in one direction, the other is correct in the other direction. So that's some good examples to figure out. Okay. Okay, I still want to go through Assign R&S quickly. Okay, so it's on the page 51 of discussion menu. I'll go to discussion menu first. Okay, so you are getting into concept. Even you don't think about this for any of the week, just during the next week. You don't need to think about that, but it will still be a learning curve easier. Okay, on page 51. I don't know if it's the same on your. Okay, Assign R&S. Okay. We will talk about what is a stereocenter, but in one sentence it would be if a carbon is bonded to 4 different groups, that this carbon is a stereocenter. Okay, so I'm sending this picture temp now. Okay, send to this one. Okay. So for example, the carbon in my hand is a chiral center. This chiral center is bound to 4 different stuff. This can be one way. And the other way would be if I change this blue, change the configuration of this blue and orange. These two are 2 different compounds. We didn't figure out these 2 compounds will have exactly the same formula. Until the second I pour the bonds up, that you can feel that these 2 are different. Otherwise, just from the formula, there isn't. But these 2 are completely 2 different compounds. So that's why we need to assign R and S. One of them is R, the other is S. And let's go to the method of assigning, okay? And that's why it's important. On the priority table, the nomenclature table I sent you, that's why I like to teach R&S here. The priority also works here. You need to assign the priority for the 4 different groups that this carbon is bound to. Assign priority here. Priority. After you assign priority to the 4 different groups that this carbon was bonded to, also using that table, but more of the time you are just comparing carbons. Okay, it's nice if you have something like hydroxyl group that is obviously a higher priority. But most of the time you will just be counting. I'm comparing a carbon bonded to 2 carbon or a carbon bonded to 1 carbon. So that table helps, but will be some exercise in the future. Okay, after you assign priority, okay. So here, if any have clear a higher atomic number, that's a higher priority. If there's something even more complicated, go to that priority table. So that's why I like to teach these 2 together. Okay. After you assign priority, you write the compound in this wedge dash format. There always going to be a group that is pointing into the paper, which is dash. That I'm writing here. When you put the least priority group in the back of the paper, which in here number 4, you always put number 4 as the lowest priority. Okay. So after you assign the priority for the 4 group that's bound to the same carbon, put the lowest priority group in the back of the paper and count if the rest of the priority group are clockwise, which is R, or counterclockwise, which is going to be S. This is something our discussion menu, but this is definitely a part of nomenclature. And that's the most common mistake, that students write the correct direction, find out where is the lowest position number, do everything correct, forget to assign R and S. So that's why I need to teach it here. Okay? Alright, so that's here. So see stereochemistry in iopide nomenclature. And more or less, okay, let's go to my notes so you guys can see. Okay, so let's go to my notes. Step 1, rank priority. For example, the blue carbon that I'm pointing to. Okay, I write out, okay. And if there something higher, like the example that I used, hydroxyl group, is definitely a higher priority. But another common mistake that students make during assigning R and S is they didn't compare neighbor by neighbor. In this case, although you see OH that's bound to this side, doesn't mean this side is always going to be ranking in higher, because it's still like when we are comparing lower position, the lowest position number. When you see a difference, the game is over. In our case, blue hydrogen definitely is going to be the lowest position, lowest priority. So it's pointing into the paper, it's in the back. And then this red carbon is bound to 3 hydrogen. This green hydrogen is bound to a CH3, a CH2 bound to something else, I don't know, okay? They're all bound to the same blue carbon, so I don't count them. So CH3 and CH2 bound to something else. Well, this yellow carbon, although it's bound to OH, I see the OH here, but when you count this yellow carbon, it's bound to only 1 CH and 2 hydrogen. So during the computation between this green and yellow, there is already a winner, which is the green carbon. Although on the side of yellow carbon, there is a higher priority group, OH, doesn't mean this yellow carbon can win this computation in assigning priority. So the most common mistakes is students didn't compare neighbor by neighbor. Whenever you see a difference, the game is over. Only if these two were completely the same, exactly the same, then you compare the neighbor's neighbor until there is a difference. Make sense? Okay. You don't even need to think like you don't need to exercise on this. I just want to make sure you see this one, you see R and S during the time that I'm teaching nomenclature. So in the future, whenever you write a name for organic compounds, you remember you need to write R and S to check if they're R and S. I teach them together, so you should write them together. Make sense? Okay, on discussion menu, next week, I assuming you will learn a little bit of R and S, then we will start to talk about stereochemistry. Okay, I teach differently. Your week 5 is also going to be squeezed, so next week is week 4, right? So I will squeeze a little bit of the discussion menu content to teach something that I think is a better plan. So be prepared for that, okay? Okay, I'm going to hand out the quiz, and our quiz starts exactly at 7:15.